Hello viewers and welcome to a new STM32 World video. In this video I am going to introduce our new STM32 Programmer / Debugger called the Jolt Connect. As usual, please like and subscribe down below, and I love reading your comments and I usually reply to every single one of them, so please post some comments as well. And this video is going to be in a couple of separate parts, 3 parts I think I planned in my head. If you get to a part that for some reason you think you know already or you're bored with it, you can look at the chapters down below and you can skip to the next section. That is okay. Please watch the video to the end. However, there might be some important stuff that I'm going to say later. In the first part of this video, I am going to talk about ST-Link devices. An ST-Link device, in my opinion, is absolutely essential if you're going to do any serious development for a STM32 microprocessor. I'll explain in section 2 why I think that is, but let me talk briefly about my history with ST-Link devices and to make you understand why I have reached the conclusions that I have reached. So first, let's look at ST-Link devices. This is actually a photo of the physical first ST-Link device I had, which is or was, I don't know where it is, I still have it somewhere, I'm sure. This is the official ST-Link, and it's got a, I think it's a 20-pin connector without any silk screen or print or legend on the box. So it is, every time I have to use this, I have to look it up and figure out how. It is also relatively limited. It's called an ST-Link version 2 device, and I quickly got tired of that and bought some of these. These are very popular. It's a Chinese clone. It's got nothing whatsoever to do with ST microelectronics, except that whoever made these took the firmware from the official ST-Link device and put it into these nice little boxes. Now, what I like about these, and the reason why I ended up always using them, is that they have this print on the box so you can see which pin it is what. And that is very, very helpful. At the time I bought these, they were around $1, so I think I bought $10 worth of them, and I still got them lying around. I rarely use them these days, but I still have them. And they work, generally, they work okay. I have, I think I had a few of them that at some point refused to update. They don't use ST microelectronic MCUs, and they use a clone MCU, and at some point some of them stopped updating. I don't know why. So anyway, it's been a while since I looked at them. They're also rather limited. They can do the flashing, they can do the debugging, but they don't have the serial wire output signal, so you can't monitor, get print out that way, and they don't have a serial port, so if you want a serial debugging, you have to hook up an extra device. Because of that, I started looking at the Nucleo boards. The Nucleo boards actually have a ST-Link device up on the top here, and that ST-Link device that you see there, you can break them off and you can actually use them as a standalone ST-Link device. That ST-Link device works really well. That is called an ST-Link / version 2-1, the firmware that is in this. And the beauty of the ST-Link version 2-1 is that it also have a virtual serial port. So you can have serial port, and you can have debugging, and you can have the SVO pin at the same time. unfortunately, I mean, you can get these Nucleo boards. I think the cheapest one is about $10, and you could break this out. Unfortunately, it suffers from the same problem. I don't know why ST Microelectronics don't like Silkscreen. Why didn't they print here? They wanted to put a Nucleo logo there. Instead, print what these pins are for. You still have to look them up. It might be printed on the reverse side, I'm not sure, but it is maddening, to say the least. So at some point, I got tired of this, and I decided to make my own ST-Link device. And I made these. Now, the reason why they have this size, I think I had a picture. No, let me flip. I have it here. So I decided to make my own devices, and they have a separate web page on my STM32 World Wiki. So I made these boards. Now, the format, the physical size and format of this board was originally made so that it will fit into one of these aluminium sleeves that the Chinese knockoffs come with. And they do. However, I never used that because on the flip side, you can't see that here. I don't know if there's a photo later on. Oh, there is here a photo that show. What I do is I have the silkscreen on the back side of the board, and it is, the pinout is not identical with the Chinese knockoffs because I have more pins on this. So on my STM32 programmer, I have 5 volt, and I have on the other side, so I have 2 pins, this is 5 volt and 3.3 volt supply. I have the power, it's called, that is to monitor the target voltage, so you won't try to flash if that target voltage is too low. I have ground. I have the clock and data in out pins. These are the single wire, serial wire debug pins that are necessary. I also have the SVO pin. I have a target reset. If you hook that up, that's optional. And I have a serial port, transmit and receive signals down here. These pins up here is for flashing the programmer itself. So it's like, this was the very first version. I think I'm on revision F or G at the moment. I can't remember the last one. What is the last one I documented here? Revision G. So there must be a revision D out there. But F actually worked okay as well. Version F was produced. Okay, so revision G is the latest one of these. Now, these devices I've been using them for way over, I think the first one was 4 or 5 years ago I made the first one, and I use them all the time. I use them whenever, for example, black pill boards, which I kind of like. It's a cheap Chinese development board, and I like them. And when I use that, I'll hook up one of my own STM32 programmers, and I'll hook that up with a jumper lead. I usually have some lying around, but just hook them up with these, and it works perfectly well. Now, let me get bigger. That is here. You can see what I'm doing. Now, these devices, I never really, a couple of my friends have some, but I never really thought about them as a production device. They got 2 problems. First of all, the USB-A connector, I will have to hand solder that in, because it is quite hard to get a manufacturer. I mean, DLC PCB would do it if I asked them nicely and pay them money for it. But the worst problem is this IDC connector that is soldered on the edge. I'm using a 1.6 millimeter PCB here, and the distance between those pins are more than 1.6 millimeters. So soldering wise, they are a little bit tricky to put on, and I don't know if you can see this, but this one is actually angled a bit. It's not really nicely aligned. So yeah, they were a bit troublesome. I think this is a revision F. Still got the mouse bites where I broke off the frame. So I never really intended to produce these or start selling them because they simply physically was not very nice. They are, however, perfectly functional, and I use them every single day or something equivalent of that. So with that in mind, I started looking into how would I make the perfect programmer, and that is what now has become the Jolt Connect. I have one here, which is a bigger PCB, got plenty of space. It's got USB-C, which can be placed by the, can you see that? Well, it's a little hard. But there's a USB-C connector here. It's got a cover, which is also a PCB, and on the cover there is a silkscreen that explains every single pin, so it is very, very easy to hook up. The idea is, let me show you an example. The idea is that here I'm simply using single wires. I have a small board here with a display. This will be the topic of a later video, and it is hooked up to one of the Jolt Connect devices here. I have made a page on the, it is linked from this, please see the new one. So I have made a page on the wiki with the new Jolt Connect. You can go there and see the documentation for it. You can see my videos about this. I have ordered, the first batch was actually sponsored by GLC PCB, so please, there's a link down in the description. Please go to that. They'll give you a coupon of, I think, $70 if you are a new user. So it's quite attractive. You can make your own PCBs, very, very attractive pricing, and have it fully assembled. So if you look at this one, this comes fully assembled except those standoffs or spacers and the screws. So I get two parts. I get the fully assembled board and that lid, and I just screw it together like this. It takes a minute to do that. So that is the new Jolt Connect, and I am going to, it's documented here on this page. Now I'm going to go through a few more sections in this video. I'm going to talk a little about the features that you have in this, and I am going to talk a little about the flashing, because one of the issues with these, if you buy one of these Chinese knockoffs on AliExpress, they will come preloaded with the ST microelectronic proprietary firmware. I'm not going to do that. That would be, well, I'm not sure that ST Microelectronic would care about it, but I will care. It wouldn't be legal. It would be stealing the software. However, I make my hardware and I make it possible for the end user to flash whatever firmware into this device that they choose to do. And should they choose to use ST-Link, that is perfectly fine with me, and I'll even explain how you can do that. But as I delivered, there will be no proprietary ST microelectronic firmware in these devices. I guarantee you that. I have my own bootloader, and this is explained in an earlier video. I can link that in the description down below, so go back and watch that one. Next up, let me talk about ST-Link and why an ST-Link device, an STM32 Programmer and Debugger, is absolutely essential for development. Now, embedded development is very different than, say, developing a game or something like that. I would say on an average embedded programming project, Maybe 20% goes into research, reading data sheets for peripherals, like for example my relay board here. All these relays are controlled by an I2C, I2C IO, GPIO expander in the center. So you need to understand the communication with that GPIO. So there's a lot of research, there's a lot of reading data sheets, etc. involved before you even get down to programming. You also need to understand the hardware that you're actually programming for. Why did that get all tangled up? You need to understand the hardware. So you need to understand which GPIOs are connected to what, whether you design your own hardware or you are using some hardware somebody else designed. You need to understand how that is put together. That research is at least 20% of a full project. Then you get down and dirty and do some programming. And I would say that takes less than 20, probably 10 to 15% of the entire project time is done doing programming, and the remaining 70% or so, or 60% of the project is figuring out why doesn't it work as you intended? How can it be optimized? How can it run better? What are the problems? How do I solve these problems? It's all, and that is the process I would call debugging. This is how to, you find the bugs, you make them go away, you check, you control, you test, and all that. That is more than half of the entire project time. And during that process, a debugger or programmer debugger is absolutely essential, which I'm going to show you now. Now, I have an example in what I'm going to do now is I have this relay board and I have hooked up one of those new Jolt Connect, and you will see here why I'm using the IDC connector. I can just do a straight I2C. I don't have to worry about what connects where, and everything is connected up. The serial wire debug signals are hooked up, the SVO pin is hooked up, and a serial port is hooked up. So let's start by looking at the serial port. And over here in this window, just verifying that I actually have a serial port running. I could test it works. So there we go. So this is the serial output sent from the relay board, and you can see it's doing an I2C scan here. It finds the GPIO expander and it just starts dumping up a tick every second, and it shows the date and the time, which is not set at the moment. So it starts at 0, and it just works. So what can I do with a STLink device or an STM32 programmer? Well, first of all, I have fired up the STM32 Cube Programmer, which is an application you can download from ST Microelectronics site. And you can see you can actually here, you can connect to this device. You will notice down in the lower left hand here that it will stop when I connect. There. Oh, it did not want to connect. Let me try to, I don't know, I've been doing something else on this. So let me try to reconnect this. It is reconnected. Let me try to connect. So now it is connecting. Okay. I should still be able to use this one, but let's try to disconnect. There, it will start up. And if I connect, it will actually stop. But when I disconnect, it will reset and start up again. You can see that here. So let's connect to it. And here you can see the flash memory, and you can, oh, it's not, I can't get much out of that, but let's do an example of what you can do in here. You can actually do a mass erase, for example, well, let me show you this first. You have these registers that you can program. For example, you have the readout protection. You can make sure that nobody can read your firmware, and pull that out by setting this readout protection to BB or CC. CC is non-reversible. BB can be reversed, but it will erase the memory if you are trying to do so. In fact, let's try to do this. Right now, we can read the flash memory up here. Now we can go down to these Option Bytes, OB. I was thinking, what does OB mean? Option Bytes, it says so up here. Let's try to set this readout protection to BB, right? Which is explained up here. So we apply that. So now the Option Bytes successfully programmed. So okay, now we can go back and read. It will still show the last read, but if I click read now, data read failed. So you can no longer read the memory. If you try to disconnect and connect again, you are allowed to connect, but you cannot read the data. Now we can go to the option byte and we can flip this back to AA, but notice what happens when you apply that. It should succeed, but notice it takes a while. It has been successfully programmed, but if we now go up and read the flash, which we will be allowed to do, you can see the flash is empty. So right now this is like a factory chip. It has never been used. There's no firmware in it, and that is about it. So let's disconnect. Let's kill this. We don't need that anymore, and let's go into STM32 Cube ID. And I have the firmware for this device here. And of course, the first thing you can do, and that's why it couldn't connect before, by the way. I had the debugger running in this. My bad. So let's try to flash this firmware. Before we do that, let's go down here. We already have the serial port running. So let's try to flash this firmware using the STLink. Here it will compile and it will wait for the debugger and it will flash. It will erase whatever was in there and it will flash a new one. Now let's look at the serial output and you can see it is up and running again. So when you are developing firmware, I go through this process hundreds of times, right? You make a change, you flash, and you see how it's running and see that everything is working. I usually, when I design my own hardware, I usually put a lot of LEDs on it, and to be honest, those LEDs are mostly for my consumption, so I can see what the hell is happening while it is running without having to fire up a proper debugger, which I could and which I will if I have to, but it is convenient to have some LEDs. I just look, oh, okay, that's what happened. I almost always have a LED that I am blinking in the, if you go to the main, where are we? No, I'm too low, it's up here. In my main loop, I'll usually print out a tick, and I will also usually, where is that? There, I will blink a LED every second. I mean, every 500 milliseconds it will turn on or off, it will toggle it, and the main reason I'm doing that is I can just take a quick glance and see if it is running, because if it wasn't running, if it isn't running, that LED will stop blinking and I will know that there is an issue or something happened and I can go in and investigate that. If it is blinking, the while loop, the endless loop, main loop, super loop, or whatever people tend to call it, if that is running, that LED will blink and I will know that nothing is hanging. There could be something else being called in this that is hanging, and that will also stop the main loop, master loop, from happening, and that means I can see what is going on. That was the basic, just flash the device, but the and I have now demonstrated flashing, and I have demonstrated the serial input-output, which is built into this STM32 programmer, the Jolt Connect. But it's got a bunch of other tricks up its sleeves. First of all, it's got the debugger. Now, a debugger is, in my opinion, absolutely essential. So the way the debugger works, rather than flashing, I can click this one. It is a little bug, and I can click on that icon, and it will fire up a debugger, and it will stop the execution at the beginning of the main. That means it has done all the memory initialization, yes, that, and it has reset the memory, it has put the stack to 0, everything is ready to execute, and it calls the main. Now, the first feature we can do here is that we can single step through this. We have out over here, we have step into and step over. Step over is F5, F6, sorry. So if I click F6 now, it will single step, and now it will jump down hell in it, and I can try to click this, press F6 and press F6 and press F6, and this already, when it goes through this initialization, is a good way. If you make a bug in one of these peripherals, it will probably hang here or go into the fault, and if it goes through it, and here we have the print. Now, if we look down there, it has not printed out anything yet. This is from the last boot, but if I press F6 now, and press F6 one more time, it has printed out those two statements that we were executing. So we can single step through the to the source code here. You will notice that over here we have a bunch of variables that we can show. So there it read boot count from the little file system, and it set the boot count to 51. It has not. These are still optimized out because I haven't reached the loop yet. But that was the speed test, and let's see the result of that. So it was writing 100 kilobytes to the it's a W25Q128 chip that is on this board. So it's a serial flash chip. It was an EEPROM. Yeah, well, no, it's a flash. It's not an EEPROM. Flash have pages. EEPROM, you can change every single address in there if you like. So that is single-step debugging. We can also do something else. We can set breakpoints. Breakpoints are really useful. Let's start with a simple one up here. You can see if now is bigger than next tick, then it will do this. So let's try to set a breakpoint in here. Toggle a breakpoint and then start running. Now it will run there. And you see now is at this point it is 2027. So it's 27 milliseconds late doing something else. Loop count is 0. Next blink 500,000. So let's try to run again. And it will stop again, and you can see now and what next blink, next tick is at this point, and how many loop count. So you can keep doing that. It will stop every 500 milliseconds. It will stop at that. So let's remove that breakpoint. You can also set breakpoints in other source codes. Let's see, for example, here. If we set the values, we have this This is the GPIO expander. I can set a breakpoint down here, and I can stop, and I can start the debugger again. There, and I can start running. You see, now it is, oh, there it came. So let's continue. Wait a second, I want to show you this. You can also monitor, now the processor is actually running, and if I look over on my board, I have the blue LED, and it is flashing every 500 milliseconds. So this part of the code is not reached. I can also go over to live expressions. While it is running, I can monitor any global variable inside this, and you can see here this UV tick, which is a millisecond since start, is happily chugging along and updating every 1,000 times every second. You can also watch the registers inside the MCU. I think you have to pause to actually see the values of that. There you have. So you can monitor registers, you can monitor the peripherals inside the chip. They are over here. You can see the I2C, you can see all the registers in that bus. It is useful to figure out what is going on, but it's also a very good learning experience, because when you're doing something in your source code, you can set a breakpoint, and then you can see what actually happened in the registers when you did this particular thing. So you have live expressions. When it's running, you can pause it and you can start it again. We can pause it and start again. So this is the debugging part, and it is a hugely complicated topic. I covered it to some degree in an earlier video. There is one more feature I want to show, because you might need your serial port for something else. You might actually need the serial port as part of your project. So there is another option for printing information out. So let's look at, I made a change here. First of all, I made a function up here, which I call serial wire out write. I think that's what SVO stands for. And I basically, you can print out any character string to this using SVO write. And then down in my main loop, where are we? Oh, not long enough. Here, you can see that rather than printing out my tick as I normally do, I print it into a string S, and I print S out, and I also send it to SVO write. So when this is running, let's run it again, you will see my serial port down here is happily writing those serial, that tick every second. But you also have built into STM32 CubeIDE, you have this serial wire viewer. I think that means data console, and you can see the SVO print there. So you don't actually need a serial port. You can use this to debug inside STM32 CubeIDE. You can debug, so you can send your print to a serial port, you can send it to the SVO, and both is working. I can briefly show, let me pause this. Down here, what is happening is you configure this over here, and you basically have these, they call them ITM stimulus ports, and port 0 is that serial wire output. You can also monitor variables. You can enable a data trace, so you can follow a trace. It actually, I'm not going to show in this video, but you can actually print a nice graph using, and it's built into STM32 CubeIDE. It is not all that useful, and I never, but you could enable here and say any address, or you could just print out UV tick if you want. The last feature that I do want to show you is if we run now, you have another feature. I don't know if I enabled it. I didn't. So if you enable sampling up here, and let's fire it up again. It should be possible to, you go up here, window, show view, there, statistical profiling, that is the one I was looking at, and we need to record that, and that is the one. So let's try to run again. It is running. Let's try to pause. There. So you can actually see how did the program flow go. It's profiling. So you can see this one, it spends about 75% in the main loop, but the rel-tick function spends about 26% of 25% if I said 75, and you can see some time is spent in the systig handler, and the ITM sendchar is using this much. The UART wait for flag is called, and this is it. So you can statistically see where is the time spent in your software. So let's try a little more elaborate example. Let's terminate this. And let's start it again so we get all the flash stuff. I don't know what that was. So anyway, it's running. Let's do the statistical profiling. It is recording. So let's start. Yeah, let's start. Let's let it run for about 10 seconds. Oh, yeah, well, that should be good enough. Let's look at the statistical profile. You can see I used a lot of time in the HAL SPI. Oh, I think I said I2C earlier. That is the GPIO expander. The flash is actually SPI. So you can see it spent some time in SPI to write. It did a speed test in that, and there's even some HAL delay. I don't know where that is, but never mind. So that is about all I'm going to say. I have made earlier videos on debugging. Go back and watch those. If I remember it, I'll link them down below. But this is basically some of the things that the Jolt Connect can do for you. Just this little device. You can do this on a black pill, you can do it on a blue pill, you can do it on whatever development board that you have access to. I mentioned earlier that I am not going to deliver these with ST Microelectronics proprietary STLink firmware. But if users want to flash that themselves, that is their deal. I'm not going to mess with that. So I'm going to show you how I flash these devices to prepare them to be sold. It is a little bit of a process, but you can do that yourself as well if you have another ST-Link. So what I'm doing now, I have a fresh ST Jolt Connect device here, and I have another Jolt Connect device where I have hooked up the the single serial wire debug, and I have hooked it up to I don't know if, let me make myself bigger here. I have hooked that up to a standard pin header, 10 mil, 100 mil pin header here, and this pin header fits into the programming port on the backside of the Jolt Connect. They're not labeled on the outside, but they are, I think, labeled on the PCB itself. So it is not. So what I'm going to do is I'm going to hook up. I have another one. Let me disconnect that to avoid confusion. So I'm going to hook up this Jolt Connect here, the red light goes on. That means it's ready. And then I simply take this. Let me be big here. I simply take this header, and that will fit nicely into, it goes that way, into the programming header there. I need to look. Oh, I don't. It is not overly dangerous. It will, and you can see now the red light actually flash on the target board. And it is now hooked up. I can do a, let me try that here. I should be able to do a, now I have to do this with one hand. I can do an ST-info probe, and you can see it sees the target device, which is an STM32F103. Now, I have made my own DFU bootloader because the STM32F103 does not have a device firmware update DFU USB. It's not built into that MCU. So I have made my own. Now the firmware for those, the binary firmware for those, will be linked on the web page. There is, okay, I have only put the jump binary. It consists of two binaries. The DFU bootloader, which will be loaded at the top of the flash, and then a jump that jumps up to that. So I have down here, I have one command that will first erase the chip. Oh, I'm big. There. It will first erase the chip. So you didn't see that. Okay. Then it will flash the DFU binary at the top of the flash, and then it will flash the jump at the bottom of the flash. So let's try to run this, and I'm just holding this in place in the header. We can do a probe just to see that it's still running. It's still there. It can still see it. And that means we should be able to run this. And let's see what happened there. It first did a complete using software reset, and it did the erased. It flashed all the erased all the flash, and then it flashed one binary, and then it flashed the other, and ended with jolly good in each time. So now this is at a state where it will be when I am delivering these. Let's try, just for fun, to hook this into. It will not work as a programmer or debugger right now. It just have that USB bootloader, and that means you can just hook this device into a USB port, and you can see current maker's Jolt Connect DFU has been plugged in. It says under me, so you can't see that. Can I? Yep, now you can see it. USB device detected. Current maker's Jolt Connect DFU has been plugged in. And that is it. That is how we are going to deliver these devices. In the next section, I'm going to show you how to flash this device and actually make it useful. Now, making the Jolt Connect device useful, we need to flash some firmware into it. There is a couple of different firmwares that can be flashed into this device that will both work. One is the STLink device, which I'm going to flash now pretty much using standard stuff that you can download from ST Microelectronics website and a bootloader. Now, the STLink itself consists of two parts. It's got a bootloader, which allow the update of the actually, and then it have the actual STLink firmware, which is separate from the bootloader. So first step to make this work is the bootloader. Before, I had the device and I connected it to USB, and it came up as a DFU device. So now we are going to flash the bootloader into this device. Not our bootloader, but the ST Microelectronics STLink bootloader. Now, if we look at the Jolt Connect webpage here, I have linked that down here, flashing installing the bootloader. Now, the installing the bootloader is a matter of uploading with device firmware update USB DFU. And there is actually a web example of a DFU flash tool, and you don't need to install any software to do this. You just go into this web page, it's linked on the page, and you can connect to a device. And you can see I have my Jolt Connect here, so I simply go to the Jolt Connect and I say connect. Then it will show, okay, we got this Jolt Connect from current makers, and we have this serial number, and this is a flash. And you can see the top part where we flashed this bootloader, my DFU bootloader, is not writable because it cannot overwrite itself. This is the one you're connecting to. So now, next up, we need to choose a file to flash. And I am not in the right location. I have that in... Let me find. I have a copy. You Google for it. STLink bootloader unprotected, I think you say. Then you will find it. I have it in my folder here, and you can see bootloaders. Now, if you go search for it, and I will not link it here, but there is a version 2.0 bootloader and a version 2.1 bootloader. We are going to use the version 2.1 bootloader, and it exists in a protected and an unprotected version. Both versions will work. Let's make that clear. But the unprotected version doesn't switch on the readout protection in the device, which means that it's easier to modify. You can still use the protected one and then disable the readout protection, which will erase the chip, and then you start all over again. But it's easier to work with the unprotected one. So we are going to flash the unprotected 2.1 bootloader bin. And we call it, they call it download. We download that into the device, and you will see it ends with a failure. The reason why it ends with a failure is that the device will actually reboot once it's been flashed, and then mean it's no longer a DFU. It can no longer, this can no longer connect. So now, if we look at, let's look at the, let's connect it, reconnect it again. So I disconnected. Oh, I have to go away. Give me a second. Scene to show that there. You'll see it now comes up as an ST microelectronic STM32 ST-Link device has been detected. Now, that is not true, because it is at the moment not an full ST-Link device. It only have the bootloader. In order to turn this device into a full-fledged ST-Link device, we need to flash the ST-Link firmware in it. Now, fortunately, ST Microelectronic provide an STLink firmware upgrade tool written in Java, and we can simply use that. Notice that the newer versions require a firmware already written there. We have not written that yet, but there is an earlier version which fortunately works. So, and it's still downloadable. So we can simply run that with Java. It's a jar file. So Java, yes, jar STLinkUpgrade.jar, the old version, 3.2.12 to be exact. We can open this device in update mode. Now, it will show you the bootloader version in here, and then it will allow you to select which version of ST-Link you want to flash into this. Now, I will recommend you use this one. This is the STM32 mass storage device. That is a drag and drop functionality. You can simply drag a binary over and it will flash. You can also do STM32 only if you can't be bothered with that, but then you won't have the virtual serial port. We might as well enable, for now, all the bells and whistles. So I am going to select, I wonder if this one works, but actually, both. I don't think so, but I'm using this one, STM32 plus MSD, mass storage device, plus VCP, virtual COM port. And I just tap upgrade. and it chugs along and writes just fine. There we go. Now, if I had not been here, oh, you can see it here, USB, now it is an STM32 STLink has been plugged in, and you can see it comes up as a disk drive, which I can mount, and then you can just drag a binary file over to that disk drive to write it to the device. And that is about it. We can now kill this one, and we don't need that anymore. We now have a fully fledged ST-Link device, although a very old version of it. The final step necessary to bring this up to date, and also as a proof of concept that this actually works, I will go into STM32 CubeIDE. Now, in STM32 CubeIDE, under the help, there's an STLinkUpgrade, which they sometimes force you to use to get to the latest version. Now, this is a lot newer version than the one I used before, but just this is the latest version, STLinkUpgrade number 3 is 16.9, and I can open this device in update mode. Here we go. Now, a feature here is I can change the type. Remember, it popped up with that disk drive I could mount and put off. I never use that feature. You can, this is a mass storage. I never use that. So I usually go in and say change type, and then I just go to this STM32 debug plus virtual COM port. I like the virtual COM port, and I can click upgrade. It will now upgrade the ST-Link firmware to the latest version available from ST, and next time there's a CubeIDE coming out, it will upgrade to that version as well. That is it. Let me remove my face, and you see it's been plugged. It's been removed when we started flashing, and then it now detects a new version, and that is it. We now have an up-to-date ST-Link device that is exactly like it would be on a Nucleo board, 100%. That's it. The final thing I'm going to mention in this video is how to now turn our Jolt Connect from being a ST-Link device into a Blackmagic device. Blackmagic is an open source firmware available completely open source, which have the debugger built into the device, so you can communicate to the debugger with the debugger using a standard serial port. It will show up not as a ST-Link device, but as two serial ports. One is the serial I/O, and the other one is communicating with the debugger, which is built in here, which can then be used to flash a target device. I'm not going to go through how to use the Blackmagic in this video. That will be covered in another video. But for now, let's just turn this into a Blackmagic device. Before we move any further, let's look over here and sudo ls usb. You can see I have my, where is it? There, we have the ST-Link device. Let's, it's okay for now. I have it there. I have the kernel locking. So let's try to turn this into a Blackmagic device. And we can do that with a little piece of firmware that the Blackmagic people behind Blackmagic provide this, which is called an ST-Link tool. Now, the ST-Link tool will take a working ST-Link, it will flip it into bootloader mode, and then it will use that bootloader mode to flash their own firmware in there. So let's run the ST-Link tool with Blackmagic ST-Link firmware bin. I made this earlier, and there will be a link on the wiki on how to build this firmware, or there will be a binary copy even of this. So let's try to run that and see what happens. There. it will first try to switch into, and you can see over here that, no, you cannot see that, I'm in the way. You will see it actually uses the firmware encryption, which is an ST-Link thing. They encrypt their firmware. I don't know why, but they choose to do that. And there we go, it is done. So now you can see over below me, there, you can see that a Blackmagic probe has been plugged in. Let's try to disconnect that. And let's try to connect a new one. There we go. So now if we do the LS USB over here, you can see that it is now, I don't know why they call it Open Mocha. This is how the Linux kernel detects this, but it's a Blackmagic debug probe application. And there should also be a couple of serial ports, which we can probably see if we go over here. In the kernel detection, you can see, I see the Blackmagic probe, the serial number, and it shows up as 2 virtual COM ports, and that is it. So we now have a Blackmagic device. I disappeared, but I'm back. We now have a Blackmagic device, and there is no hint of ST microelectronics firmware left in this. Now, just to demonstrate a point, it is now a Blackmagic point. Let's switch it back. So it is possible with that ST-Link tool, which I had here. You can run this. I think I can't remember. It's -P. So if you do a -P, it will switch this into DFU mode still, and we can now go back and run our STLinkUpgrade jar. We have the device, we can open it in update word, and we can upgrade it. And now we are back to the whole process again. You can go earlier in the video, and it is now an ST-Link device. So this device, the Jolt Connect, can be switched between ST-Link and Blackmagic probe. Once we get the details about how to sell these devices sorted out, I'll recommend you buy 2 of them. You can have one, and if you break one of them, you can use the other one to flash the first one. It will buy 2. I will strongly suggest you buy 2 of them. Also, shipping will be a fairly big post for most people, so I would suggest you buy 2. But this is all I intended to say today about the Jolt Connect. Where is it? I had it here. The Jolt Connect. I hope that we will put these up for sale very, very soon. The exact price is not determined yet, and we also need to produce a bigger bulk of these. I don't know how many we are going to produce. We'll see. It is still under investigation and under, yeah, well, it'll come soon. But please comment down below and let me know if you like the idea. It will be the ultimate flexible STM32 programmer and debugger. And I'm actually very pleased with how it turned out, and I am quite sure that, where is it? Probably not going to use the old one very much anymore. It worked fine, but the USB-A irritated me a bit. Every cable I have now is USB-C, so I was quite happy to no longer use the USB. I had the extension cable with a female connector in one end, and it's like they get dirty and they don't work real well. USB-C is much, much better. That's about it. As usual, have a wonderful rest of the day.